All right, let's talk about the invisible shield that protects your car the very second you turn it on. Secure Boot. This is the bedrock, the absolute foundation that makes sure your vehicle is running exactly the software the manufacturer intended and nothing malicious.
So, here's how we're going to break it all down. First, we'll get into why this is so critical. Then we'll look at how the whole system builds trust from a single, unshakable anchor. We'll explore the tools, the challenges, and then, finally, we'll walk through how it all works in the real world.
Okay, so to really get why Secure Boot is such a big deal, you first have to appreciate the mind-boggling scale of the software running in the cars we drive every single day.
Yep, you're seeing that right. Over 150 million lines of code. That's way more software than in a modern jetliner. And this code isn't just for your infotainment system. It's controlling your engine, your brakes, your steering. Every single one of those lines is a potential doorway for an attacker.
And that leads us to the fundamental question, right? When the code running on a chip is the difference between a safe stop and, well, a disaster, how can you be absolutely certain it's the genuine, untouched code from the factory? Well, Secure Boot is the answer. Just think of it as the ultimate bouncer at the front door. Before any piece of code is allowed to run, it has to prove it's on the list. Secure Boot checks its ID, and if something's off, it stops malicious code dead in its tracks.
But here's the thing. For any security check to actually mean something, it has to be based on something that is itself 100% trustworthy. And this brings us to the most important component in this entire system, the root of trust.
The analogy here is just perfect. If you're pulling on a heavy chain, you need to know that very first link is bolted to a solid wall. In the world of cybersecurity, that unshakable, unmovable anchor is what we call the root of trust, or ROT.
And for this anchor to really hold, it has to be basically perfect. It must be physically unchangeable, what we call immutable. It needs to be simple because complexity is always the enemy of security. And most importantly, you can't be able to just walk around it. If an attacker can bypass it, the whole system just falls apart.
And this slide really drives the point home. The root of trust isn't just some abstract concept. It is a physical thing. The code is literally burned into the silicon chip itself, using memory that, once you write to it, can never be changed again. That permanence, that's your ground truth.
So, you've got this solid-as-a-rock anchor in the hardware. Great, but how do you extend that trust out to cover those millions and millions of lines of code? Well, you forge a chain, one link at a time. This is the chain of trust in action. The unchangeable root of trust runs first, and its one and only job is to check the very next link, the first bootloader. If that link is secure, it passes control. That bootloader then checks the next piece of code, and so on, creating this unbroken chain of verification all the way up to the apps on your dashboard. Now, in a modern, complex chip, this whole process gets even more sophisticated. You'll often have a dedicated security processor, a hardware security module, or HSM, that acts like the bootmaster. Its entire job is to securely start up all the other processors, each of which could be running its own operating system for a totally different task.
So you might be asking, why not just check all 150 million lines of code at once? Well, that's called a monolithic approach. It's simple, but it is incredibly slow. You can't be waiting a full minute for your backup camera to turn on. That's exactly why cars use a staged boot, verifying only what's needed at each step to get you on the road quickly and safely.
So what are the actual tools, the nuts and bolts, that make this verification possible at every link in the chain? Well, it all comes down to a really clever mix of cryptography and specialized hardware.
These three crypto tools are really the workhorses of Secure Boot. A hash function creates a unique digital fingerprint for the software. A digital signature proves who created it, the car manufacturer. And a MAC is another powerful way to check integrity, making absolutely sure that fingerprint hasn't been tampered with.
Now, pay attention because this is the most critical part of the entire system. At the factory, the manufacturer uses a top-secret private key to sign the software. Your car has the matching public key, and it uses it to check that signature. But, and this is a huge but, if that private key ever leaks, an attacker could sign their own malicious code, and your car would trust it completely. Everything, and I mean everything, depends on protecting that one key.
And all of this runs on special hardware. You can think of a Secure Hardware Extension, or SHE, as a good basic lock. A full-blown Hardware Security Module, or HSM, is more like a complete bank vault. As you can see here, the HSM is its own dedicated security computer, which gives it the flexibility to use the strongest, most up-to-date crypto algorithms as new threats emerge over time.
Now, in theory, Secure Boot sounds just about perfect. But like with anything in engineering, actually implementing it in the real world is incredibly challenging.
These are the kinds of things that keep security engineers up at night. A single mistake, like allowing an attacker to force a rollback to an older, more vulnerable software version, can completely unravel the entire secure boot process. Each one of these flaws is like a crack in that shield we talked about.
And it's not just about avoiding simple mistakes. It's a constant, tricky balancing act. You need rock-solid security, but you also need the car to start up fast. You've got to secure multiple complex processors, sometimes from totally different companies, all under one cohesive security plan. It's a massive engineering puzzle.
Okay, so let's put all the pieces together. I want to walk you through a typical secure boot process, from the factory floor all the way to your car's dashboard.
This whole story starts with the manufacturer. They take the final software, they create a cryptographic hash of it, that digital fingerprint we mentioned, and then they use their ultra-protected private key to sign that hash. This whole signed package is what gets programmed into the car's memory chips. Okay, now flash forward. You get in your car, you press the start button. The very first thing that happens is the processor starts running code from its unchangeable ROM. That's our hardware root of trust. That code can't be modified, so it's always trusted. The root of trust's first job is simple. It needs to create a brand new digital fingerprint, a hash, of the next piece of software it's about to load from the car's memory. Then comes the moment of truth. It uses the public key that's baked into its hardware to check the manufacturer's original signature. This one single check confirms two vital things. One, that the software is authentic, and two, that not a single bit has been changed since it left the factory. And this leads to a critical fork in the road. The signature is either valid or it's not. There's no gray area, no in between. If the signature is valid, the chain of trust continues and control is handed to the next link. But if it's invalid, the system immediately goes on lockdown. The boot process might be halted, access to sensitive data gets denied, or the car might enter a limited safe recovery mode. In short, the car protects itself.
So let's just quickly recap the big takeaways. Secure Boot is all about providing software authenticity and integrity right at startup. It's totally founded on an unchangeable hardware anchor, the root of trust. It extends that trust through an unbroken chain of verification, and the entire strength of that chain depends on one thing: protecting the manufacturer's private key.
And this leaves us with one final, pretty important question. Secure Boot does a fantastic job of establishing a trusted state when the car turns on. But that's just the beginning of the story. Modern cars are always connected, they're always receiving data. So what's protecting the car after the boot process is finished? Well, that's a topic for another day. Thanks for joining me.